So for this section 5.1, eigenvalues and eigenvectors, that's the primary, we're going to discuss the primary tool we need to solve systems of differential equations. And guys, even though there are a few methods to solve systems of differential equations, such as well, this one that I'm about to present, also we can use substitutions to like, as if we were solving any system just regularly. We can also solve systems of equations, systems of differential equations using the Laplace transform, which we will do later. Yeah, we'll do. But now for now we're going to solve systems using matrices, eigenvalues, and eigenvectors. Okay, what are we going to do here? Let's talk about the concept of linear independence and dependence, which we already discussed a little bit about it when we were looking at the theory of the higher order differential equations. All right. So number two, we're going to define what eigenvalues and eigenvectors are. Number two. And number three, compute those eigenvalues and eigenvectors for some given matrix. Okay, guys. So what we're gonna do should look familiar from that chapter two in higher order differential equations, except that we're no longer talking about functions being linearly dependent or independent, but rather vectors. So we're given a collection of vectors of n vectors with n components. Denote those vectors like x1, x2, x3, dot dot dot, xn. All right. So we can form the following matrix: big X, uppercase X, which is whose entries are column vectors denoted as x1, x2, x3, dot dot dot, x sub n. Okay. What should look familiar from before if we compute the determinant of this matrix, and if it's not equal to zero, then the n vectors in the set are linearly independent. Otherwise, if the determinant is zero, then the n vectors are linearly dependent, which means we can find constants c sub 1, c sub 2, etc., c sub n, such that multiplying those constants with those vectors, we get the zero vector as a result. That's one. Or number two, one of the vectors in the set can be written as a multiple of the other vectors. So that's another way to explain this linear independence and dependence. Does that remind you of something from before? The Wronskian, right? That's essentially the Wronskian. However, the Wronskian was very specific for these vectors in the form of functions, exponentials, polynomials, trig, you name it. But in this case, this theorem just is just related for vectors in general. For those of you who are right now in linear algebra or have taken it before, well, there's a bunch of things that can be vectors, not just those directed arrows with components. No, even functions, polynomials are vector, could be vectors under certain conditions. Matrices are vectors. Anything, it's a vector, even cows or chickens can be vectors under certain conditions. Well, that was kind of weird, but well, that's something for a linear algebra class. All right. Yeah, I wish I had that picture, but anyway. Okay. So, well, we're as examples to check this linear dependence and independence of vectors. Let's determine whether the following sets of vectors are linearly independent or linearly dependent. And well, we're given for letter A, vector x sub 1, which is 1, 3, with entries 1 and 3, and vector x sub 2, with 2, negative 6. Well, at first glance, I mean, in some cases, the cheating way, in a way, is to check if one of the vectors is, at first glance, a multiple of the other one. And well, it doesn't seem like, right? It looks like negative 6 is a multiple of 3. Oh, well, 2. Hmm. Yeah, well, they're multiples. However, the sign is messing things up, right? If they were both negative here for like negative here, or maybe a negative here, well, then we have a linearly dependent system, well, or set rather. What do we do in this case? Well, so let's form matrix big X, okay? Matrix big X equals to x1, which is the vectors 1, 3, and vector x2, which is 2, negative 6, okay, and find its determinant. So the determinant, big X, equals, so not parentheses, not brackets, just like absolute value bars, 1, 3, 2, negative 6. And again, just like the Wronskian, guys. Essentially, we're calculating the Wronskian, but we don't call it the Wronskian for numerical vectors. So 1 times a negative 6, that's a negative 6. Minus 2 times 3, is that negative 6? What is negative 6 minus 6? Negative 12? Conclusion, this is not equal to 0, right? This is not equal to 0. So this means, therefore, x1, vector x1, and x2 are linearly independent. Linearly independent. All right. Well, letter B. For letter B, we have three vectors in R3. Also, notice how I'm playing with the notation. While for part A, I use parentheses to denote. I'm using brackets for the vectors in part B. Doesn't matter. Same notation, different notation. They represent the same thing. Okay. So what do we do? Write a matrix big X with these vectors being the columns of the matrix. Okay. That's 1, negative 1, 2, 2, 3, 0, 4, 1, 4. Okay. Well, what are we going to do? We're going to compute the determinant here. That is the determinant of big X. That'll be bars 1, negative 1, 2, 2, 3, 0, 4, 1, 4. Here we go. Oh, I'm going to use Cyrus rule for this one, right? I mean, if you want to use expansion by cofactors and minors, okay, go for it. That's fine. All right. So, I mean, as long as you get the same results, that's fine. Oh, let me repeat. 1, negative 2, and 2. Oh, wait, negative 1, 2, 3, 0. What is that equal to? So, what is 1 times 3 times 4? Is that 12? What is 2 times 1 times 2? Is that equal to 4? Plus 4. And 4 times negative 1 times 0, that's a 0, plus 0. Minus the backwards by diagonals or secondary diagonals. 4 times negative 1 times 2, is that negative 8? 1 times 1 times 0, that's a 0. 4 times 3 times 2, is that equal to 12 times 2, which is 24? So what is that equal to? 12 plus 4, is that 16? And minus 24 minus 8, is that another 16? Oh, this is equal to 0. What does that mean? These vectors are actually linearly dependent. That means we can find constants C1 multiplied with the first vector, C2 multiplied with the second vector, C3 multiplied with the third vector, such that the result will be the zero vector. That's one way to see it. Another way to see it is maybe x1. Okay, we can find a way to express x1 as a combination of x2 and 3. Maybe we can find a way to express vector number 2 as a combination of vector 1 and 3. Or we can find a way to express vector 3 as a combination of vectors 1 and 2. That's what it means. All right. So these are linearly dependent. All right. So that being said, well, why is this important? Because we want to make sure that our solutions to these systems of differential equations are precisely linearly dependent. So we need to check for this. Okay. So now let's talk about these so-called eigenvalues and eigenvectors. Well, right now I'm going to be technical with the definitions. But actually, what they represent or even applications, I'm going to mention those at the end of the section. Okay, so let's suppose we have a square matrix of size n by n. And then we have another matrix, an n by one matrix. Well, that's more properly called a vector. All right. So, and okay, so if we multiply those together, A with V, that is A, V, what is that going to be equal to? It's going to be equal to whatever, okay? For now, it's a whatever. But the thing here is, since this matrix is square, it's an n by n, and this column vector, this vector is an n by one. That is n by one. So that means we can multiply those two matrices, even though B is a vector. But again, a vector is technically a matrix. We can multiply these two together because the number of columns in A is equal to the number of rows in the vector. And then the result will be an n by 1. All right? So when we multiply, the result will be an n by 1 vector. So, but the question here is whether it is possible to for that new vector to simply be some constant times v. That's that's the big point here. Okay, so it turns out, but this is true under some special situation. So let's have a look at this definition. Let's develop the idea of the eigenvalues, eigenvectors, and of course, do some examples. Okay, so let A be an n by n matrix with V be an n by 1 vector and lambda be a constant such that AV equals lambda V. Then lambda is called the eigenvalue of A, and V is the corresponding eigenvector. These two always come in pairs, right? This comes in come in pairs, okay? All right. But what are they? You might wonder. Well, we'll talk about their more geometric physical meaning later when we're done with some examples. For now, let's develop this idea. Okay. How do we know or how do we find these eigenvalues and eigenvectors for a given matrix? Well, there are two things that we need to keep in mind before we can figure this out. So we need to know a couple of facts. We need to keep in mind a couple of facts. All right. I mean, of course, we're not going to prove these facts. Actually, these are facts from linear algebra that we will simply use for. Otherwise, I mean, that would be a whole semester, right? That's why. Okay, so a matrix A is said to be singular if its determinant equals to zero. So those of you who are in linear algebra or have taken it before, it has to do with finding the inverse of a matrix. So if its determinant it is zero, then that means we cannot invert that matrix. We cannot find the inverse of that matrix. That means it's singular. The matrix equation AX equals to zero. Notice the bold case because what do we have here? A matrix which is a collection of vectors, whether row vectors or column vectors, however you want to see them. That X is another vector, and the result is the zero vector. Okay, so this matrix equation will have exactly one solution, that is x equals to zero vector, which typically we call it the trivial solution um, if A is non-singular, right? If it's non-singular. Or it will have infinitely many non-zero solutions if A is singular, all right? Okay. So given these facts, let's develop a method to find the eigenvalues of the matrix A. So let's consider the following. So again, A vector V times V has a vector equal to lambda V, which is another vector. Okay, so that's what we want to. So we're looking for those values that times this vector equals the matrix times the vector. Okay, so I'm going to treat this like an equation. Well, in fact, it's an equation. Let me move the lambda term to the left hand side. So A V minus lambda V equals to zero, but in this case, it's the zero vector, not the zero constant. We're working with vectors. Okay, we're working with n by n vectors. All right. So, I mean, here is the thing. okay, clearly there is a common factor here, which is this vector v. Okay, so and I would like to factor it. However, if I do so, okay, don't write this yet. Do not write this. This is a minus lambda. What do we have there? Uh, we're in a big situation there because A is a matrix. It's an n by n matrix, right? And lambda is just a number. So we will have a size problem with the matrix being an n by n and lambda just essentially a one by one matrix, which is just a number. So let me go back. Okay, there's nothing to see here. Okay, go back. So I'm going to turn that lambda into a matrix that matches the size of A. How? How about the multiplication by 1? How about if we multiply anything by 1, the value of whatever we're multiplying by 1 doesn't change, right? So I'm going to multiply by, okay, the second term, okay, AV first, minus lambda. How do I multiply a vector by 1? Multiplying by the identity matrix I sub n, all right? Let that be equal to the 0 vector. And finally, I will factor out v and define this. So av, I mean, a minus lambda I sub n times v equals the 0 vector. All right. So we're so we just treat this equation like the what's it called? Like the zero product property. You know, uh, this is equal to the 0 vector if this is equal to 0 or v equals to 0, but we don't want v to be 0 actually. So actually, we have to let this guy equal to 0. But wait a minute, this would be a matrix equation. We want to know the determinant of a minus lambda I sub n equals to 0. Notice this is the number 0 because the determinant outputs a number, not another vector, not another matrix. Okay? So this is the process to find, this is the equation we need to find, we need to solve in order to find the eigenvalues. All right? So once we have the eigenvalues, we need to go back to find the corresponding eigenvectors. So the summary of the equations we're going to use for this process is number one, the eigenvalue equation. So we're looking for numbers, not vectors, not matrices. We equal to 0. Once we get the eigenvectors, I mean the eigenvalues, go solve the eigenvector equation, which is this one right here. All right, and find the vector v related to whatever lambda. So again, as mentioned, these eigenvectors that I highlighted in yellow are related to their eigenvalues, right? They go in pair. All right. To give you an idea of how this works, before we get to actually calculate any eigenvalue, let's let A be this matrix 1, negative 2, negative 1, 0, and some vector V, 2, negative 1. The question here is V an eigenvector of A? How do we know that? Well, let's put this into the eigenvalue equation, the initial equation that is. So let's start with, in other words, we want to show whether these two matrices satisfy somehow the following condition, that is AV equals to lambda V. All right. So let me perform the product. 1, negative 1, negative 2, 0, times v, which is 2, negative 1. Is that equal to lambda times 2, negative 1? Okay, so let's perform the product of the matrices on the left-hand side of the matrix equation. Again, 1 times 2 equals to 2. Okay, maybe. Okay, number 1. We have a 2 by 2 matrix and then a 2 by 1 matrix. What should the resultant matrix be? A 2 by 1, that's another vector, right? You'll see how everything is going to make more sense now. So let me multiply 2 times 1, which is 2, plus negative 2 times negative 1, which is actually positive 4. And second row with the column, negative 1 times 2, that's negative 2, plus 0 times negative 1, is that negative 2? Let that be equal to lambda times 2 comma negative 1. Well, compare the vector on the left-hand side with the vector on the right-hand side. Are they multiples of one another? It seems like if we factor a 2, okay, so if we factor out 2 out of the vector on the left-hand side, that's going to leave us with 2, negative 1 equals to lambda times 2, negative 1. Now, how do we know these two matrices actually satisfy that condition? Because do you see the same vector v right here? Do you see the same vector v? Okay, well, then that is true. So v equals to negative 1 is an eigenvector of A with eigenvalue, will be the eigenvalue lambda equals to 2. All right? Yeah, right now. Yeah, I know it's kind of weird, or all we're doing right now is kind of weird, but finally, because where did that come from? Well, actually, that's the next topic here, to actually find eigenvalues. Okay, guys. So now we're given a matrix. All right, go for it. Find the eigenvalue or eigenvalues and the corresponding eigenvector or eigenvectors. The reason why I put parentheses to make it singular and plural, that's because some of these eigenvalues could be repeated. So we may have only one eigenvalue. All right. Okay. So what do we need to do to get the eigenvalues? First of all, solve the eigenvalue equation. So first, let me define the matrix A minus lambda I. Okay, so A minus lambda I, which is A, which is 0, 1, negative 6, 5, minus lambda times I, the identity matrix. Okay, and well, so let me multiply the second matrix by lambda to get everything in terms of a simplified matrix. Okay, that is 0, 1, negative 6, 5, minus lambda, lambda zeros everywhere else. And combine these two matrices together. So this will be 0 minus lambda. Oh, come on. 0 minus lambda and 5 minus lambda. And then the other entries remain the same, negative 6 and 1. Okay, so that is for the eigenvalue equation. Now, what do we do? Find the determinant of this matrix we just got. The determinant of A minus lambda I, let that be equal to 0. That's going to give us the eigenvalues. All right? Okay, guys, for that first step I just did, I'm gonna do this only once for this exercise, but in the future, all for in practice, all we do is simply subtract lambda from the elements along the main diagonal to make this quicker. But I showed you one full process just so you can see how that relates to A minus lambda I. All right, let me write this down. So that the determinant is the bars, 0 minus lambda, that's negative lambda, and then negative 6, 1, 5 minus lambda. And let that be equal to 0. Okay, so a 2 by 2 matrix, for 2 by 2 matrix elements along the main diagonal, that is negative lambda times 5 minus lambda minus negative 6 times 1. Let that be equal to 0. So let me continue up here because I'm going to need the space. Continue up here. Okay, this is going to give us negative 5 lambda plus lambda squared minus minus is plus 6 equal to 0. Let me just arrange in descending order of powers. Lambda squared minus 5 lambda plus 6 equals to 0. And guys, this polynomial we obtained here is called the characteristic polynomial. The polynomial that's going to give us the eigenvalues. And well, I mean, here is where our factoring techniques are going to come to play. Well, so how about the double bubble method? Factors of positive 6 that add up to negative 5 at like negative 2 and negative 3. Do you guys agree? And that means the eigenvalues are lambda 1. We call this lambda 1 equals to 2. And lambda 2 equals to 3. Okay? So now let's find the eigenvectors. That is the eigenvector corresponding to lambda 1 equal to 2, and the eigenvector corresponding to the eigenvalue lambda 2 equals to 3. Okay, so for lambda equals to 2, what do we have? What do we have? Okay, what's the eigenvector equation? Okay, guys, we're gonna go back to this equation right here. The eigenvector equation say same matrix A minus lambda I equals to V. However, you already know the value of lambda, so now you need to substitute. We need to substitute the value for lambda. V right here. That's actually the vector to be obtained, right? That's the vector to be found. How do we do that? Well, let's set up the equation first, okay? So, I mean, guys, this is going to be quite a bit of notation. It's very important that you follow it. So, number one, I'm going to go with A minus 2 times I, okay? Okay, let me go with, yeah, A minus 2I times V equals the 0 vector, okay? Well, let me write this as a system of equations. So, this matrix, right? We're going to use this matrix as a starting point to now substitute this lambda. So the the elements along the main diagonal. So now they're going to be 2, or rather 0 minus 2, and then 5 minus lambda, which is 2, 5 minus 2. The other two elements, 1 and negative 6, remain the same. I'm going to multiply by the vector, let me call this v1 and v2, which is the eigenvector we were looking for. And let's set this equal to the 0 vector represented by this matrix here. Okay, guys. Let me simplify this. And well, do you guys agree that this is really a system of equations in matrix form? If you multiply the results of simplifying this, that'll give you whatever number v1 plus whatever number v2 equals to 0. And then a second equation, whatever number v1, I mean, plus another number, whatever number times v2 equals another number, in this case, 0. So to be lighter on the notation, I'm going to write this instead as an augmented matrix. What's an augmented matrix? Well, write down the simplified entries here, 0 minus 2, that's a negative 2, negative 6, 1, and then 5 minus 2, that equals to 3. I'm going to draw a bar right here and zeros to the right of the bar. So the entries to the left of the bar represent the matrix in the matrix coefficient, while the right side of the bar, that's the right hand side of the system of equations. And guys, here there's a lot we can do. We can reduce the matrix using matrix operations or your calculator. However, there's no need to do that, because in a way this is already simplified. What I'm going to do here, I'm going to highlight the easiest of the rows. What do I mean by that? The easiest of the rows, this is the row. Okay, so this second row here is telling us the following. It's telling us that 1 times v1, v1 times 1 plus 3 times v2 equals to 0. Okay, let me solve for the easiest of the variables. In this case, I'm going to solve for v1. v1 equals to negative 3 v2. Why am I doing, guys? Because I mean, you don't want to verify for every single exercise. If you reduce these matrices, you will always get matrices that encode systems of equations with infinitely many solutions in which one of these entries, V1 or V2, can be given any number, any parameter. All right. So, and I want to skip all that. I'm going to go straight to just grab one of the rows, write it as an equation, and check this out. Okay. I'm going to let V2 equals your favorite number, guys. Your favorite number. Doesn't matter which one. I'm going to choose 1. Okay, V2 equals to 1. That means V1 equals to negative 3 times 1, which is negative 3. So the eigenvector V with entries V1, V2 has components negative 3 and 1. For the eigenvalue of lambda equals to 2, we have the eigenvector, the corresponding eigenvector, negative 3, comma 1. All right? Guys, the choice of one may not work every single time. We may need to choose any other number that may not be one, like a larger integer, because in some cases we may get rational coefficients. And if you don't want to use fractions, well, keep use. If you want to use fractions, keep using one. If you don't want fractions, use a number that divides out the denominator, and that's fine. Uh, why do we have this freedom of choice of any of the numbers? Okay, again, these vectors get scaled, all right? While the scale, and it doesn't matter whether that vector has components negative 3, 1, or negative 6, 2, or negative 9, 3, or negative 150 and 50. It doesn't matter. The length of the vector doesn't matter. Multiplying a vector by a constant, by a scalar number, doesn't change the direction of the vector this is going to, only changes the magnitude, and that doesn't really matter. The magnitude is fine as long as it doesn't change um, the direction. We're fine. Okay, so that was the eigenvector for lambda equal to 2. Okay, what about the eigenvector for lambda equal to 3? Okay, so for lambda equal to 3, what do we have? Okay, um, again, let's write the eigenvector equation. A minus 3i times b equals to the 0 vector. That means the original matrix, to the original matrix, we're going to subtract minus 3, to subtract 3 along on the elements along the main diagonal. So 0 minus 3, which is um, 0 minus 3, and 5 minus 3. That's the elements along the main diagonal. The remaining entries, negative 6 and 1, remain the same. This times the vector v1, v2, and let that be equal to the 0 vector. Okay? Now, I'm going to turn this into an augmented matrix system that represents the system of equation. That's more compact, easier to handle. I mean, so 0 minus 3, is that negative 3? 1. Negative 6 and 5 minus 3, is that equal to 2? Oh, wait. Bar and zeros to the right. Okay? Now, have a look at this. Well, one thing, the reason why I know, again, these systems of equations are going to have infinitely many solutions. It's because if we were to multiply, say, okay, for the previous system, multiply the, okay, divide the first row by 2 to get negative 1, negative 3, and then add it with the second row. The second row will become all zeros. All right? That's what happens. Same here. If I multiply, say, the second row by 3, for instance, and combine the two rows together, that's going to give us the 0 row in the zeros bottom row right here. So, and I know I'd rather skip all that and simply grab the simplest of the rows here. If you want to do the first row, I mean, they're multiples of each other anyway. All right. What does that represent anyway? So again, the first column, it represents the coefficients of v1, that is the coefficients of x in a regular system, if you will. The second column represents the coefficients of v2, or the variable y, if you will. All right. Now, what is this? Yeah, so that means 1 times v1 equals to v1 plus 2v2 equals to 0. Again, I'm going to solve for v1 equals to negative v2, and v1, oh, I'm going to let, again, v v2 be any number. The simplest one, the better. Let it equal to 1. Okay? That means v1 equals to negative 2 times 1, which is negative 2. And now we have the components of the eigenvector corresponding to lambda equals to 3. All right? Okay, so that being said, okay, let's see. So um, v, which is v1, v2, that is negative 2, comma 1. So this is the eigenvector corresponding to the eigenvalue of lambda equals to 3. All right? Okay, guys, if you're wondering at this point, what the hell are these eigenvalues, eigenvectors? Okay, let's go to the last page of the handout, and then we go back to the next exercise. Okay, so what are these eigenvalues and eigenvectors? Okay, so the interpretation of these eigenvalues are simply scaling factors. That's all they are. Associated with a matrix's eigenvectors, which are special vectors, okay, that only change in magnitude, like I mentioned. That's why we had that freedom of choice for the value we want to do, right? And well, this change in the magnitude results into a stretching or a shrinking of a vector, depending on the number we multiply such a vector by, but actually that doesn't change the direction of a vector. Okay, as discussed when the matrix is applied to this value. Okay, so an eigenvalue tells us how much a matrix stretches or compresses a vector, and it can also represent a flip if the eigenvalue is a negative number. Okay, let's go to this example right here, guys. Remember this preliminary example, no, right here. So this eigenvalue lambda equal to 2 gave us such change in the magnitude when change, no, not the magnitude, well, yeah, the magnitude when multiplying the matrix times the vector, we actually got the same vector that it was claimed to be that eigenvector, but we got it scaled by 2. So what does that matrix do? Scale that eigenvector, right? That coefficient, that numerical value is the eigenvalue. That's what it is. Numerically, that's what it is. Now, applications, where do you see these eigenvalues and eigenvectors in engineering, structural or mechanical engineering? So these are used to determine, to determine the natural frequencies and modes shapes of vibrating structures, like in bridges and buildings. In electrical engineering, they're applied to analyze the stability of control systems and designing optimal controllers. In aerospace engineering, they use eigenvalues and eigenvectors to use for flutter analysis and spacecraft attitude control. In computer science, these are used a lot in image and facial recognition, like on your phones. When you set up your phone to unlock it using your face. All right. These are used for coding, such because an image actually creates a matrix of the colors of your face, and the shape creates a matrix with the shape and the colors, and that's what they do. Google's page rank, so the algorithm that ranks web pages is based on the eigenvalues of a matrix that represents the website link structure. So they're quite a bit there. In physics and mathematics, quantum mechanics, eigenvalues, and eigenfunctions. For those of you in chemistry, you're going to get to this in physical chemistry. These are fundamental when calculating expectation values and analyzing quantum systems. Pretty cool stuff to do. In differential equations, which is what we want them for, to solve systems of linear differential equations. That's what we want them for, right? And dynamical systems, which are the next step to this, to describe the stability of a system, identifying the modes of expansion or decay, because usually these systems of equations relate a growth and decay system, all right? And in other fields, like in economics, we use these eigenvalues and eigenvectors to analyze complex systems, predict the long-term behavior, and understand system dynamic and equilibrium states. Those of you in linear algebra may have talked about what's it called? Stochastic matrices, when you have a situation of different let's say these different cell phone companies or different uh, fast food chains, so how many switch from one service to the other, or how many as percent they do, so they do switch from one or the other. Well, that's actually those matrix multiplications you did gave rise to these eigenvalues and eigenvectors. But back then, they didn't tell you about that because you were barely learning the matrix operations. Well, now you have an idea of what they are. And of course, in the market risk analysis, these are used to define if a matrix is positive, definite. Well, that's more economics and that's something else. All right. Okay, so let's see about the next example. You know what? I don't think I'm going to have enough time in 5 minutes to solve it, but at least I wanted to give you the idea of what eigenvalues and eigenvectors are with us, so you guys don't get out of the classroom and ask yourselves, what the hell is going on here? No, at least, yeah. All right.